Hi, we will continue with the formulation of the power flow calculation problem. In this lecture, we focus on two learning objectives. The first one concerns with the definition and evaluation of power flow equations, and the second one concerns with the identification of network node types. In power flow calculation, the Y-bus matrix, voltage phasors, and nodal currents work together to describe the system. The Y-bus matrix represents network connections. Voltage phasors define the magnitude and angle at each bus, and nodal currents are computed from their relationship. Together, they allow calculation of power flows, voltages, and system performance. The formulation of power flow calculation considers that active and reactive power injection equations are derived using the relationship between the Y-bus matrix, bus voltage phasors, and nodal currents, starting from the complex power at each bus is expressed as the product of voltage and current. So, substituting the current from the Y-bus relation and separating the real and imaginary part gives the nonlinear equations for active and reactive power in terms of voltage magnitudes, angles, and Y-bus elements, which are then used to solve the power flow problem. Next, each node is characterized by four key quantities: active power, reactive power, voltage magnitude, and voltage angle. These variables are interconnected through the nodal power injection equations, where active and reactive power at each bus depend on the voltage magnitude and angle, as well as the network connections defined by the Y-bus matrix. Since not all four quantities are known at every bus, some are specified while others are calculated, allowing the equations to be solved and the system's operating condition to be determined. To structure the problem formulation, the buses are classified as slack, PV, PQ, based on known and unknown variables. The slack bus has known voltage, magnitude, and angle, while its active and reactive power are unknown. So, no power equations are solved for it. A PV generator bus has known active power and voltage magnitude, while reactive power and voltage angle are unknown. So, one active power equation is used. A PQ load bus has known active and reactive power, while voltage magnitude and angle are unknown. So, both active and reactive power equations are solved. Summarizing, a slack bus has no equations to solve since both voltage magnitude and angle are specified. A PV bus requires one equation, active power, to be iterated, as voltage magnitude is known and reactive power is adjusted. A PQ bus requires two equations, active and reactive power, since both voltage magnitude and angle are unknown as must be solved. Let's now illustrate the structuring of equations with a simple example concerning with a small-sized synthetic power system having a 4-node transmission network that interconnects 3 generators and 1 load. For instance, the bus 1 can be assumed as a slack bus or slack node. So generator G1 is set to define the reference voltage phasor of the system. G2 and G4 are considered as PV generators, so buses 2 and 4 are PV buses. The location of the load entails that bus 3 is considered as a PQ node. Hence, there are 3 active power injection equations related and 1 reactive power injection equation to be iterated and solved, for instance by using the Newton-Raphson method. The outcome of power flow calculation concerns with the values of the voltage phasor magnitude associated with bus 3 and the voltage phasor angles of bus 2, 3, and 4. The unknown active and reactive power injections can be determined from these outcomes and the relevant elements from the Y-BOSS matrix. To sum up, in this video, you have learned about the formulation of the power flow calculation problem, as well as the rationale behind the identification of the network node types that is needed to structure the power equations to be iterated.